Now there was formerly a picture up here which I got rid of because there's no way you would be able to understand that picture without me actually constructing it. So I'm going to kind of construct it. I have 1, 2, 3, 4, 5, 6 points here, and I want to construct this vector field at these 6 points, showing the development of the vector field, just to give you an idea of why you have a curl and what that curl means. Okay, so first of all, each of these vertical dotted lines is for constant x, and x on this dotted line is less than x on this dotted line. Now, whatever the x component of any of these points is, we're going to multiply the negative of that exponent by the j vector to get one component of the vector f, one vector component of the vector f. Well, okay, so at every one of these points, x here is less than x here. So x is going to be the same at all 3 points here, so negative xj is going to be the same at all 3 points. So I'm just going to say, okay, let's say that negative xj looks like this. And at these 3 points, x is quite a bit bigger, so negative xj is going to be a lot bigger than it was. Okay, so what I've drawn in yellow is negative xj for every one of these points. Now, what good color do I have here? I've got purple, which contrasts pretty well with yellow, so I'll use it. Now, we're going to also do yi. Okay, and y, of course, gets bigger. It's 0 here, so our yi is going to be 0 for both of these vectors. We're not even going to draw a yi. But then y is bigger here and even bigger here. Now, at these 2 points, y is the same, so that yi is going to be the same. So if I want to draw yi, let's say here yi looks like this, and up here y is bigger, so yi is going to be bigger. Not really doing this very well to scale, not missing it by that much, but we get the idea. So the y being smaller here is going to be smaller here and here than it is here and here where y is bigger. Now we have the resultant vector. Here the resultant vector is just going to be like this. You know, we just draw the components. Here it's like this. Here it's like so, and here it's like so. And here, well, the resultant vector, y is 0 both here and here, again, so we have no yi, so our vector is just going to be the same as our negative xj vector. Okay, so what's going on with these vectors? Well, you can kind of see if these are the velocities of a field, that those velocities tend to take whatever the field is and rotate it around the y-axis. It's rotating this way and then this way and then this way. And if we go into the fourth quadrant, well, you should actually extend this. You know, 2 points here, 2 points here, and then 2 points over here and here, 2 points over here and here, and really draw the field so you'll understand what this field looks like. So you have an ability to draw fields and a better ability to visualize fields even if you don't draw them. Now, what did we do in the problem? We calculated the integral of this curl, or of this field, around the unit circle. Now, I don't know where 1 is on this picture, but let's just say that right here we have part of the unit circle. So here we go from here to here. Let's just say that's the arc of the unit circle, at least in the first quadrant. And remember, we're going counterclockwise because of our right-hand rule, as we talked about here. So, what do our tangent lines look like? Gee, I don't have any orange. Yeah, I do. Okay. What do our tangent lines look like, and how does that relate to our vector field, as in green? Well, our tangent lines would look like this. These would be our DRs. Okay, this might be one delta r vector, which approaches a dr. And what's the vector field do? Well, the vector field isn't exactly, well, maybe it is exactly anti-parallel to delta r, but it's clear if we're moving in this direction that we're moving against this field. So that what we're measuring when we do this integral is the fact that the field is rotating against our path around the curve. And has a significant component against that path. So the rotation of the field relative to our path along that curve is negative. Well, what did we get? We got negative 2 pi for the integral around the entire circle. So that should make some sense out of this. Now, as far as making sense out of the curl of f, there's a little more we'd have to say, some things we need to understand better about the curl to understand why that curl is negative 2k. So let's just stick with our calculation. And so we won't really talk too much about the area integral of the curl. That's a little bit difficult to understand. If you understand the circulation, it gives you a really good start on the curl. Then you can kind of ponder what it means to integrate the normal component of the curl over the surface. And you have to relate that with Green's theorem. It's several steps that you have to put together to understand that. And many of you are adept enough with this stuff and have been able to work hard enough on it that you might be able to make some sense out of that. But at this point, we're going to be content to understand the idea of a curl as a circulation and understand the mechanics of Stokes' theorem.